Okay, so this is a review paper by a big group, the who's who of the Cliver uh, committees and some other groups. They all come together and put together these big papers called reviews, and it appears in this journal called Frontiers. I think you can figure out these journals. They are quite expensive from what I heard, but anyways, toward an integrated pan-tropical ocean observing system. Toward an integrated pan-tropical ocean observing system, obviously they look at what exists, what is needed, what are the gaps, and it depends on whether you are looking for long-term global warming type of processes or sustained observations for large long-term changes, or uh, forecasts at shorter time scales, weather and climate, or you're trying to do, including also ecosystems and other things and so on and so forth. Obviously, they want, when they say integrated, obviously they mean everything. And I'm going to be brief, there's a lot of text. Let's start by reading the longish abstract. Global climate is regulated by the ocean, which stores, releases, and transports large amounts of mass, heat, carbon, and oxygen. Understanding, monitoring, and predicting the exchanges of these quantities across the ocean surface, their interactions with the atmosphere, and their horizontal and vertical pathways through the global oceans are key for advancing fundamental knowledge and improving forecasts and longer term projections of climate, weather, and ocean ecosystems. The existing global observing system provides immense value for science and society in this regard by supplying the data essential for these advancements. The tropical ocean observing system, in particular, has been developed over decades, motivated in large part by the far reaching and complex global impacts of tropical climate variability and change. Started with the paradigm of ENSO, El Nino prediction in the tropical Pacific, extended to the Atlantic, then to the Indian Ocean, and so on. Okay, however, changes in observing needs and priorities, new challenges associated with climate change, and advances in observing technologies demand periodic evaluations to ensure that stakeholders' needs are met. Previous reviews and assessments of the tropical observing system have focused separately on individual basins and their associated observing needs. Here, we provide a broader perspective covering the tropical observing system as a whole. Common gaps, needs, and recommendations are identified, and inter-basin differences driven by socioeconomic disparities are discussed. And building on the concept of an integrated pan-tropical observing system is what is the story. So there are previous reviews which were, Pacific Ocean, Indian Ocean, Atlantic Ocean. They want to consider all of them together and also pay attention to who can install them, maintain them, service them, and so on and so forth. So finally, recommendations for improved observations of tropical basin interactions through oceanic and atmospheric pathways are presented, emphasizing the needs and benefits that can be achieved through closer interbasin coordination and international partnerships. So we call them oceanic tunnels. So there is the Indonesian through flow between the Pacific and the Indian Ocean, which plays an important role at all time scales. And you have atmospheric bridges like the Walker Cell and the Hadley Cell. So if you have an integrated pan-tropical observing system, then you can see what those interactions would look like. So I'm going to run through a bunch of figures to start to place ourselves in context, and here is a good one to start with. This is the annual mean ECMWF reanalysis era 5 zonal and vertical winds. So you can see trade winds and the maritime continent with tremendous convection and rainfall, and then you have subsiding branches on the western Indian Ocean over here, and of course over the Amazon you have some convection, but you have also subsidence and clear skies and less rainfall and so on in the eastern tropical Atlantic. So let's read that just to be sure. This is average between 5 north and 5 south, which is typical of pan-tropical studies when you look at meridional mean zonal cells. This is the World Ocean Atlas 2018 ocean surface temperatures in colors. So here we are looking at black arrows are zonal and vertical winds, and vertical wind speeds are in colors. So positive numbers, of course, vertical upward. Typically pressure decreases, so you would tend to have omega, the pressure velocity, to be negative going up, but here we are just following the standard wind speed convention, and arrows are showing the vertical motion anyway, so I don't know why I mentioned it. So you have specific currents here. This is the annual mean. You know, this circulation completely flips here, but do annual mean and you get something. It's convenient to do annual means, but it's always tricky if you use the same concept in the Indian Ocean, because the currents and winds reverse quite significantly. Whereas here you have again trade winds. So Indian Ocean, you can see in the annual mean shows some mix of winds, whereas here you have trade winds, and then you have monsoonal winds penetrating in here. So you have south equatorial current, coastal currents here, north equatorial countercurrent, north equatorial current, and the western boundary currents, Indonesian through flow here, and you have somewhat similar structure in the Atlantic, slight differences in terms of the size of the basin and so on. If you look at the vertical section here, depth versus longitude, obviously Pacific dominates with its clear structure of upwelling, uplifted thermocline, which is similar to the Atlantic, but you can see because of the zonal scale you have a warm pool accumulation of warm waters in the deep tropics, which of course sloshes back and forth during an El Nino, and you have Indian Ocean, which is actually got a thermocline tilting the other way, so you can see thermocline is shallower on the west and deeper in the east as opposed to the other two basins and so on, which are all basics that you probably already know. So these have to be observed, and you have to also include what's coming through here and what's here, and what's its impact on here, not only in the ocean, but eventually you will have to also do how coupled air-sea interactions may grow, because slight anomaly of ITF from here, Indonesian through flow, can start off air-sea interactions and growing modes here off of Java, and then of course it can extend equatorward as Indian Ocean dipole, and you have a similar Atlantic La Nina here, Atlantic Nina, sorry, and so on. These are the SST anomalies, and from the Hadley Center, so I won't read the details of the data. Near surface winds from ERA 5 and rainfall from global precipitation climatologies. So green are positive numbers and brown are negative numbers. Contours shown for 0.75 millimeter per day regressed onto the index of the dominant near equatorial mode in each ocean basin for 1980 to 2023, which means Atlantic Nino, IOD, and El Nino. So you can see the positive IOD is when you have cooling and drier, less rainfall here, and you have warmer and more rainfall on this side. El Nino, of course, has a typical warming and cooling structure. All these are changing, and they all, so this peaks in December, January, February, the September, October, November, June, July, August, and so on. There are various details in terms of processes, etc. What is the lower one? We are looking here at, so you can see, let's rainfall in global precipitation climatology regressed, etc. Indian Ocean dipole, El Nino and Atlantic Nino, each normalized by its standard deviation. In B, it's same as A, except for the Indian Ocean basin mode, Pacific meridional mode, and the Atlantic meridional mode. So you have zonal modes, and this is when typically season after El Nino peaks, Indian Ocean warms in this fashion as opposed to this east-west pattern, and it's called the Indian Ocean Basin mode. Lots of literature on it. Pacific Meridional mode came, I think, after Atlantic Meridional mode was first described, if I'm not mistaken. No, actually Dan Wymont et al. Described this first. John Chiang jumped on this one. There are lots of differences in terms of how the ITCZ moves here, how many times it touches the equator, how it moves here, and this tropical, extratropical interaction based on SST anomalies, wind anomalies, and responses, and then there is debate about whether this is what the so-called Central Pacific El Nino is, dateline El Nino, or is it something independent, and so on and so forth. But if you want to do pan-tropical observations, then obviously you need to capture both. These are just global tropical in situ observing systems as of January 2024. So there are moored buoys. You can see in the Indian Ocean, Rama. This is now used to be called Toga. I don't know if it's called TPOS by now. Tropical Pacific Observing System. I'm not been keeping up with the changes because a new design was made recently, and you have Pirata in here. So you have moored buoys, surface met observations, moored buoys with subsurface observations, biogeochemical moored buoys, mooring for ocean circulations, tide gauges, Argo, the float that goes up and down and measures temperature, salinity, and sometimes other things, and that's the biogeochemical Argo, for example. High frequency radars, expendable battery thermographs, and volunteer ships and other ghost ships. Ghost ship is a global ocean ship-based hydrographic investigations program. Okay, so when you look at it this way, it looks like it's quite well covered. But remember that these dots are massive compared. If you put the real size, you will not be able to see anything compared to the zonal and meridional scales of the basins. So we put big dots, and that makes it look like we have covered a lot of it. But actually, there are lots of gaps and lots of tricky things like how to monitor faster time scale things, waves versus advection, AC interactions, and so on and so forth. Okay, so looking at 1980 to 2020 trends in SST from HADA SST and rainfall from GPCP. So you're looking at trends. Again, pay attention to the scales, and you have statistical significance shown as well. Brown circles for trends less than 0, and green circles for trends. So there is warming here, and precipitation is increasing, I guess. So rainfall from GPCP, green circles for positive trends, and brown circles for negative trends. So the SST warming and cooling are shown. Of course, East Pacific has some issues in terms of data gaps, but still we know pretty well that this is warming less or even cooling compared to this, which has all kinds of implications in terms of strengthening SST gradient and ocean heat uptake, which modulates the global warming and so on. So increased rainfall here, decreased rainfall, increased rainfall overall on the western Indian Ocean and northern Indian Ocean here. Not so clear here. You have a lot of warming, maybe the Atlantic multi-decadal oscillation kind of signature over this short period of 1980 to 2020. And the bottom one here in B is SST regressed onto the Indian Ocean basin mode, Pacific decadal oscillation, and Atlantic multi-decadal oscillation, and so on. So you can see the different time scales as well. So how are they connected? That's the tricky thing, right? This PDO looks like an El Nino. This has been debated for a while, whether it's just a superposition of El Ninos and La Ninas, which are asymmetric and so on, whether this is anthropogenic or natural mode, and how natural modes are modulated by anthropogenic warming. And of course here there is a rapid warming happening, which looks like the basin mode. So here the basin mode itself is regressed onto the Indian Ocean. So SST regressed onto the Indian Ocean basin mode here, Okay, so some details, but basically I'm going to say these are the various science questions that the team is considering. Here we are looking at other important processes we want to focus on, like latent heat flux, net heat flux, shortwave radiation, and residual. And the trick is that you cannot often directly measure these heat fluxes. Shortwave you can measure. QNet is obviously a sum of shortwave, longwave, sensible, and latent. So you are measuring components, winds, SSTs, humidity, etc., to derive latent heat fluxes with bulk formulas. Sometimes you do more fancy way with covariances and so on. But nonetheless, uh, there is serious there are serious differences between different products. The residual matters because if globally you are not balancing the net heat flux, then you will be either warming or cooling the ocean, and those rates can be much larger than global warming itself, which means your data can be kind of very limited use. Okay, so indeed they are showing annual mean ocean mixed layer heat budget residual, so that itself requires a lot of assumptions and derivations, because what is mixed layer? You define it with temperature criteria, cooler than the surface by 0.1 degree, or density criteria, and so on. So there is no unique definition, but nonetheless you have to do this and figure out what the residuals are. So all these are tricky things. So you can always argue we need more data, but somehow we have to also make sure that we are doing the fluxes in a way that we can reduce errors. But for example, a lot of ocean modeling is done by using heat fluxes, let's say, then half a watts per meter squared error, or in shortwave we can have tens of watts per meter squared. And I wouldn't call them errors, but let's say differences between in situ observations and satellite estimates and so on. They are all kind of very tricky issues. So observations obviously need to continue for sustained observations and get better for closing or reducing these residuals, right? These are the examples of sustained coastal observing systems in the Bay of Bengal, maritime continent. Here in B, there have been many field experiments as well, Yahtzee and so on, Gulf of Mexico in here, and the Eastern Atlantic. Okay, so obviously there is a mix of moored buoys, surface met observations, biogeochemistry, ocean circulation, high frequency radar, and so on, that we looked at before. And these tend to be done in a field campaign mode, so you have snapshots of data, so it's hard to derive long-term things. These kind of trends are typically done through reanalysis products like here, or SST products that are a mix of observations and extending backward with other methods, etc. So obviously it's always complicated, right? So we'll read. There are a lot of recommendations that I'm not going to read, but I'm going to read the discussion, so we'll get some sense of what comes out of this long discussion. So here are gliders and USVs, and so this is underwater glider in red, and uncrewed surface vehicle USV. Data here collected from yeah. So NOAA itself is having now lots of trouble with the new administration in terms of funding and its mission, and people losing their jobs. So we don't know exactly where we are headed right now. It'll take a few years before we realize how bad things have gotten. This is the annual mean tropical cyclone accumulated cyclone energy, ACE accumulated cyclone energy during 1980 to 2023. We know the hotspots, about 30% of the total number of cyclones are born here. There are some here, North Indian Ocean of course, and Southern Hemisphere as well. And the second one here is of course number of days in a log scale with severe marine heat wave conditions during 1980 to 2023. Marine heat waves became just a concept recently, but now we are going back and reprocessing data and defining new heat waves, so you can see the number of days in log scale. So you have here El Nino signature, maybe part of the meridional mode, and Indian Ocean looks complicated here. There are focused papers written for this region as well as here. Of course, it all started over here in the Northeast Pacific. And this C is, I think, the coral. I kept reading these papers, and then by the time I'm recording, I'm forgetting. So C is maximum heat wave category experienced during 2023, which was a record warm year because of the El Nino plus global warming plus maybe reduced aerosols or underwater volcano. We don't know, but all kinds of maybe reduced albedo from clouds and so on and so forth. Heat wave categories are defined elsewhere. You can follow up, but basically you can see that 2023 really lit up the entire tropical oceans in terms of heat waves, right? You have to also look for ecological effects, because ultimately heat waves are important when they have ecological impacts, even though we don't always have data to see what else happened. But also one has to think later on how to predict them. If you predict them, what can you actually do about the heat wave? Will you stop fishing? Will you somehow find an engineering approach to protect corals, and so on and so forth? This is the CO2 flux. We know that this is an upwelling region, so you get very strong outgassing here, and you have Somali upwelling here, and some other processes going on here as well. And annual surface chlorophyll concentration here, upwelling, outgassing associated with upwelling. Coastal regions are always hotspots for upwelling, Canary and Angola, Benguela, Somali, and so on. River dynamics here complicated. This is the ITCZ wind stress curl lifting the thermocline and producing chlorophyll. This is the annual mean oxygen concentration. We know natural minimum oxygen minimum zones occur here in under the ITCZ and so on, where you have various processes combining to produce minimum oxygen, production, respiration, etc. And this region is special. You have a very huge anoxic region with all kinds of chemistry and so on going on, and similarly in the Bay of Bengal, etc. And in D, you are looking at annual mean oxygen concentration with depth average between equator and 30 north as a function of longitude, just to show how these oxygen minimum zones penetrate. This one is massive. It goes all the way down to deeper than 1 kilometer. This one also extends far south, but you can see it's beginning to disappear here, but this one continues in. Lots of papers on the physics associated with these things: circulations, dynamic biogeochemistry, dynamics biogeochemistry, and so on. So these are the global tropical BGC observing systems as of April 2024. Ships and moored buoys in the and this is the Southern Ocean something net here. Okay, BGC, Argo, and moorings. I'm running through these because these are just the discussions leading up to justifying why we need an integrated observing system. Okay, so this is schematics of tropical basin interactions, impacts of the tropical Indian Ocean on the tropical Atlantic. So you have Indian Basin mode or IOD mode, and it has increased Agulhas current, possibly southward shift of the westerlies, and you have, of course, lots of interactions happening here through El Nino and Indonesian through flow and so on and so forth. Many of these are open questions, but that can be used to justify that we need more observations. There is the Philippine anticyclone, which always plays a big role in all kinds of interbasin interactions here. And in B, why don't I see where is A, B? Maybe I chopped it off, but nonetheless, middle impacts. So they were arranged this way. I cut it off. That's all. Middle is impacts of tropical Pacific on the Indian and Atlantic Oceans. So you have cyclone anomalies, strong Walker cells, strong subtropical high, less tropical cyclones, anticyclone, Aleutian low, and so on. And you have modes here: Atlantic multidecadal, tropical North Atlantic, Western hemisphere warm pool. This is from Chunsai Wong. I forget We should look up WP here. I cut it off, but anyway, this is the Atlantic zonal mode here, and of course the Indian Ocean, and you have Pacific. This is the last one here, bottom. It's hard to bottom impacts of the Pacific tropical Atlantic on the Indian and Pacific Ocean. In other words, they are interacting strongly. Indian Ocean has been looked at a lot because it's argued now that Indian Ocean actually influences how much anthropogenic heat actually goes into the Pacific, and it also affects the Atlantic meridional overturning circulation. And of course, you have a unique Southern Ocean here, which pumps water into the Indian Ocean at a very rapid scale compared to the other two oceans. So even though our focus is here, they are all connected via the atmospheric bridges and the oceanic tunnel here. Okay, so obviously we have to keep all that in mind. So that's just kind of a run through the figures to see what are all the important processes they considered. The need for ocean observations has never been greater. The motivations that drove advancements of the tropical observing system beginning in the 1980s toga, such as ENSO and other tropical climate modes, which were used as motivations or needs, still exist, and in many cases are becoming more challenging to understand and predict because of the decadal and longer time scale modulations of their behaviors, like how is El Nino changing because of global warming, for example. The more recent efforts to bring tropical in situ observations, including surface drifting buoys, Argo floats, and moored buoys, to their target numbers took place against the backdrop of accelerating global warming and the associated fundamental changes to weather, climate, and ocean ecosystems. With the increasing frequency of disruptive climate and weather events, the demand for global tropical ocean observations will only increase. The global tropical observing system must proactively evolve and anticipate these needs, but now you know that NOAA is struggling like hell. It's always difficult to get international funding. If you want to maintain observations in the Indian Ocean, who's going to contribute? Maybe Australia and India, but US obviously has a lot of interest there. China has a lot of interest there, so maybe it's often about coordinating and working peacefully despite all the other interests such as deep sea mining, etc. Right? With the increasing frequency of disruptive climate and weather events, the demand for global tropical ocean observations will only increase. The global tropical observing system must proactively evolve and anticipate these needs. As we said, the tropics are expected to experience high rates of changes in temperatures and precipitation extremes over the next 20 years, many projections indicating this, exposing high density human populations to increasing risks from extreme events. An important finding from this review, consistent with the recent air-sea transition zone report, is that the present tropical observing system is inadequate to address the growing needs to observe, understand, and predict extreme weather and climate events such as marine heat waves and tropical cyclones. The deficiencies are especially acute in near coastal regions where the societal impacts are often greatest, and the subsurface oceans where satellite observations cannot penetrate, but also there is always tricky to get into coastal regions because there are exclusive economic zones and countries are very sensitive. Marine heat waves in particular can have severe impacts on ocean ecosystems. Currently, many of the tropical nations and island communities that may benefit the most from the observational networks are not well connected to the observing communities. Adapting the present observing system to provide the high frequency real-time observations needed to advance understanding, prediction, and adaptation will require technological advancements, international coordination, and involvement of local stakeholders. Continued innovations are needed to aid in situ monitoring, including uncrewed underwater and surface vehicles, and to expand satellite observations such as potential missions to measure total surface currents and the state variables required to estimate surface heat fluxes. So the total currents comes from the practice that has existed so far, where we measure sea levels from satellites, but they only give you anomalous currents, not total currents. Full depth ocean heat, and you can follow up the details on my other podcasts. Full depth ocean heat and carbon storage must be monitored globally, since long-term changes in these parameters strongly affect global warming and resultant changes in extreme events. A second major conclusion of this study is that global tropics are severely undersampled in terms of biogeochemistry and ecosystems, given the importance of the tropical oceans for global carbon cycle and the societally relevant changes in ocean ecosystems driven by pronounced tropical climate variability and trends. It's a wish list. How do you prioritize these things? That's a separate issue, right? It's crucial to maintain existing ship mooring and satellite-based observations while advancing BGC Argo to its optimized target density and full range of BGC sensors, light, chlorophyll, oxygen, nutrients, etc., etc. The list can keep growing. This will serve as a starting point for designing and implementing more extensive in situ biogeochemistry and ecosystem observational programs, building on the recently launched PACE program, which is Plankton, Aerosol, Cloud and Ocean Ecosystem Satellite, and the future GeoXO or Geostationary Extended Observations, which will provide high resolution, about 390 meter resolution, for ocean color and water quality data every 2 hours, with the capability to distinguish between different phytoplankton types. Right now we measure chlorophyll and say that's converted to net primary production, gross primary production, but imagine actually classifying species using these global maps from satellite. Recent advances in uncrewed and autonomous sampling should be leveraged to fill the sampling gaps left by the existing networks and to explore high frequency variability at finer spatial scales. The COVID-19 pandemic highlighted the vulnerabilities in global observing systems, including disruptions to data collection and maintenance due to restrictions on travel, ship observations, and fieldwork, as well as supply chain issues for procurement and refurbishment of equipment. The Indian Ocean Rama array, which before COVID-19 had data returns of 87%, was reduced to 2% data from the mooring in 2022. Redundancy in observations, through overlapping systems, diverse platforms, and multiple data streams, helps ensure continuous data flow even when individual components are compromised. This is a very ideal situation. Getting funding is very difficult, let alone build in redundancies with additional funding. By proactively integrating these elements into the design of pan-tropical observing systems, the scientific community can better safeguard critical ocean data and ensure continuous monitoring of climate variability, extreme events, and ecosystem changes. An integrating theme for the tropical observing system is pan-tropical basin interactions, which demand international and trans-basin coordination and strengthening of regional organizations. The challenges of understanding and predicting variability in individual basins are greatly amplified for tropical basin interactions, which require pan-tropical observations of the ocean and atmosphere on time scales ranging from intra-seasonal to multi-decadal. Again, prioritizing means this will be optimized in some other ways. It's crucial to develop an observing system that considers the ocean and atmosphere in an integrated manner, including co-located measurements throughout the AC transition zone that encompasses the oceanic and atmospheric boundary layers. That's Caroline Clayson's paper. The observing system must continue to advance in order to better understand and predict these tropical basin interactions while maintaining the valuable observing system of the present. Okay, so I ran through it because it's got some interesting points, a lot of reviews, nice figures, so you can go back and read the paper, which is quite long obviously, and lots of references because it's a review paper and it's an important pitch. And now if some government, let's say, wants to take over one ocean and wants to say give me a prioritized list, then you have to find funders for other two basins and you have to optimize them together, so it gets very tricky. This is just a pie in the sky wish list, and you can assume that it's as comprehensive as it can get, but still, if you give it to another team, they will add more things like deep sea Argo and impacts of deep sea mining and blue economies and so on and so forth. So let's leave it here. Okay, see you in the next topic.